Hi, Assalamualaikum. Hi guys. So today I will cover on chapter 3, which is internal diffusion. This chapter is chapter 12 in your textbook. So I will divide this lecture on chapter 3 into two parts. So this one is the first part. Okay. Right, these are the outcomes, the topic outcomes for this chapter. So the first one, students should be able to explain diffusion and reaction in porous catalyst. So it's internal diffusion. And then second, students should be able to define Thiele modulus and effectiveness factor. So you will learn these two terms throughout the chapter. The third one, students should be able to describe the regions of reaction limitation and internal diffusion limitations and also the conditions that affect them. The final one is the student should be able to design the reactor based on mass transfer limitation. Right, so these are the 7 magical steps in your catalytic reaction, heterogeneous catalytic reaction. So in this chapter 3, we are focusing on step 2 and step 6. As you see in the figure, is internal diffusion, right? Okay, so diffusion and reaction in spherical catalyst pellet. Okay. If you refer to figure 1, okay, this chapter is discussing on the internal diffusion. Okay, so the internal diffusion is in the sphere. Okay. Okay, for this figure 1, we can see that the reactant A will diffuse as the external diffusion, okay, from the bulk to the surface of the catalyst. So for this chapter, we will see that how the reactant A will diffuse from the external surface of the catalyst, which is the concentration is the CAS, into the catalyst interior, where the concentration is CAR at any point of in the catalyst, right? So the molar flux, if you remember last time in chapter 2, we learned on the molar flux, which is WA, okay, will depend on molecular diffusion, JA. Remember, WA equals to JABA, but in this slide, in this chapter, BA will not exist, so you will only see JA, right? So previously, JA is equals to negative DAB, DCA over DZ. So in this internal diffusion, JA is a function of effective diffusivity over as a function of concentration, and also R is a distance in the catalyst, which is spherical. We assume it is spherical, right? Okay, so what is effective diffusivity, or known as DE just now? So DE is used to describe the average diffusion taking place at any position R in the catalyst pellet. Last time it's all about DAB. So in internal diffusion, we use DE, okay? So DE is described by this equation. You can refer to your textbook, okay? Besides than using DAB, okay, we can also use Knudsen diffusivity, but somehow Knudsen diffusivity only applies at a small catalyst. So after this slide, I will show you a graph where to apply DAB or where to apply Knudsen diffusivity. Okay, so tau is tortuosity, psi p is pellet porosity, and sigma c is constriction factor. So here you can see the pores are not straight, but there are some interconnecting pores, a lot of it, and all of the pores and the path are varying. They are a varying cross-sectional area. Okay, this is the figure that I've been mentioned about. Okay, so you can see here there's a Knudsen diffusion. So this is decay, right? So it is in this part, okay? The pore radius is a smaller pore radius compared to the one that you apply is DAB. So this is molecular diffusion, okay? Right, so in order to describe diffusion and reaction in porous catalyst, we will perform a shell balance on reactant A. So you consider an irreversible reaction of A to B. Okay, so you will perform the shell balance to this part, right? Okay, so from chapter 2, we know that reaction rate, which is RA double prime, is equals to WA. So this is actually the equation why they times the surface area is just a conversion of unit, right? So we are actually considering at this area, the slash one. Okay, so now the rate of generation, okay, is actually equals to rate of reaction of the catalyst times, okay, this one. Okay, all this is actually it's just a conversion unit. Okay, right. So we do the mass balance. So this one is like the reaction one, in minus out plus generation equals to accumulation. So accumulation is 0, right? So just now for in at R, so these are the equation that we took from the previous slide. Okay, and then generation is actually the one also taken from the previous slide. Okay, so these are the steps. Step 1 until step 6 is to show you, is actually want to show you on solving the mole balance, where in the end it will arrive at equation 1210 in your book. Okay, so here, okay, if you from the mole balance you follow this step, okay, I hope that you will do some revision on it. Okay, so you will arrive at this equation, right? Okay, so if you see the boxes here, okay, this is like actually a conversion table to convert RA single prime to RA double prime. Okay, if let's say you have RA double prime, how do you want to convert it to RA single prime? Okay, so this small box in page 818 in your textbook is very important. Okay, so let's say in the question given you are a single prime, how you want to convert it into RA, so you need to times by the density of the catalyst. Okay, so here, okay, after you see equation 12.10, okay, the next slide will show to you equation 12.11. So you will arrive at this equation, right? So this is some sort of like not meaningful equation. It's not a friendly equation. So we need to simplify it. So to simplify it, we need to have a boundary conditions. The same thing that we did in chapter 2. Okay. So we put boundary condition. So if you refer to this figure again, okay, you see here the okay. The radius of the catalyst is what we call capital R. Okay, the small r is actually the radius, any part, any place in the catalyst. Okay, so if you see here, CAS is the concentration of A at the surface of the catalyst. But later you also see that CA in your catalyst is CAR. Okay, so here the boundary condition applies are these two. CA is finite at R equals to 0. So R equals to 0, we start it from the middle of the catalyst. So this is R0. So to it move towards outside of the catalyst. Okay, and then CA will become CAS at R equals to capital R. So you see here, we know that the concentration at the surface of the catalyst is CAS. So this is what the distance of the catalyst is actually capital R. So now we arrive at dimensionless form. Okay, so due to the boundary condition just now, so we will meet this two-dimensionless form, which is psi and also lambda. So psi is actually CA over CAS, and lambda is R over capital R. So if you apply the boundary condition just now, okay, this one, these two, so your psi will become 1 and lambda becomes equals to 1 at CA equals to CAS, and at R equals to R. So similar goes for the other one. Right. So from equation 12.1, 12.11, so we replace all the equation with lambda and also psi. So in the end, we get this simplified version of symbol, the new symbol, which is what we call Thiele modulus. So Thiele modulus is actually K1 R squared over dE. This is for first order. But for second order or any order besides one, so these are the formula for Thiele modulus. Right. So if you rearrange back the Thiele modulus, okay, initially it was written in this form, okay. So you rearrange back, okay, in order to show you, okay, this equation is actually, when you rearrange back, you can see this is actually a ratio of surface reaction rate to diffusion rate. So if you get your Thiele modulus large, okay, high, meaning that your internal diffusion limits the overall rate of reaction because your diffusion rate is small, okay, and then meaning that your your KR is very high compared to your KC. But if your Thiele modulus is small, meaning that the surface reaction limits the overall rate of reaction. Okay, so for first order reaction, we can simplify this Thiele modulus. Okay, so you just insert n equals to 1. So all these will be simplified as the equation in the box, right? So you have to be careful because this is a reaction rate constant K double prime. So this is the reaction rate constant of K. So this is about surface area of the catalyst. It is about the volume of your the volume of the solution. So you need to refer to your book to convert the unit. Okay, so it's stated in page 818 how you convert K1 to K double prime or vice versa. Okay. And then how the Thiele modulus correlates the relationship between Thiele modulus and psi, and also your lambda is this equation. Okay, stated it's in your book. Okay, so it's equation 1227. Okay, so you can also see here in the figure, okay, of how the Thiele modulus will varies with regards to the catalyst radius and also the concentration. Okay, and Thiele modulus for first order reaction is actually a dimensionless number, meaning no unit. So you have to, when you do a calculation, that you might make sure that it is advised for you to include the unit so that you know in the end your calculation is correct when you have a dimensionless number. Okay, so I stop here for the first part. So we'll continue on the second part of this chapter. Okay, thank you. Have a nice day.